I'm Mark Cavanaugh for Cavi Coaches, and today I'm going to coach you up on magnetic force, forces on moving charges, and current carrying wires. In this video, we're going to talk about magnetic force, forces on moving charge and current carrying wires. So magnetic force is exerted on moving charged particles. So the particles have to be moving. And the force vector is perpendicular to the velocity vector of the particle as well as the magnetic field vector. A second right-hand rule is going to determine the direction of the magnetic force vector. So we're going to use something called the right-hand rule for moving charge in a magnetic field, and it determines the direction of the force on a positive charge by the field. So that means if we find the direction of a positive charge, then it's going to be the opposite direction for a negative charge. So we have a magnetic field that is directed into the page, and we're going to send a moving charge particle into that field. So we have a positive charge. So the way we determine the direction of the magnetic force is first, we're going to align our thumb in the direction of the moving charged particle, and our fingers are going to point into the page as the direction of the magnetic field. So we align our fingers with the magnetic field, and the palm shows us the direction of the force on a positive charge. So in this case, that would be up. The negative charge would be in the opposite direction then if we use that. So we could use a left-hand rule to determine that, or we could just use the back of our hand. So we're going to look and see what happens to this particle as it moves through that magnetic field. So as we align our hand and the particle moves, we know that our hand is going to move, and we can see that that force is always going to be pointing towards the center of a circular path. And then the charge exits the field, and it's going to move in a linear path as it exits the field. So we're going to learn how to calculate the magnetic force. Remember, magnetic force is on charged particles that are moving. So Fm is going to represent the magnetic force in newtons. Q is going to be the charge of the particle in coulombs. V will be the speed of that particle in meters per second. And B is going to be the magnetic field strength in Tesla. So this is the equation you would use if the velocity vector and the magnetic field vector are at right angles. If there's an angle between the velocity vector and the magnetic field vector that's not 90 degrees, then we have to multiply this equation by sine theta, and theta is going to be the angle between V and B. So if we look at our right-hand rule, it's going to be the angle between our thumb and our fingers, which represent the speed, direction, and the magnetic field. Now, magnetic forces can accelerate charged particles, but only by changing their direction, as we saw in the previous slides. They can cause charged particles to move in a circular or a helical path. What they cannot do is change the speed or kinetic energy of charged particles, and they cannot do any work on charged particles as they move through that magnetic field. So let's look at an example problem. We have a magnetic field that is directed into the page. We have a charged particle of positive Q and a speed V that moves into the magnetic field, and we want to sketch a possible path of the charged particle as it moves through the field. So we're going to use our right-hand rule to align our thumb in the direction of the particle's motion. The magnetic field is into the page, and we can see the force would be pointing upward along our page. So as that particle moves through the field, we would see that the force and our velocity would change. So we'd have a circular path that the charge would move through that magnetic field. Again, if this was a negative charge, the circular path would then be the opposite direction. Now, if the particle has a mass of m, we want to write an expression for the radius of that particle's path. So we know that the magnetic force at the beginning is pointing up. It is the only force, and it's causing it to have a circular path. So what we're going to do is we're going to use Newton's second law, that the net force equals mass times acceleration. Well, our net force is the magnetic force, and that's going to equal mass, and the acceleration is going to be a centripetal acceleration, which is v squared divided by r. So this is the equation we're going to use to derive an expression for our radius. Now, we also know that the magnetic force is just Q times V times B times sine of theta, and that's going to equal mass times velocity squared divided by radius. We can simplify this equation because we've got v on both sides, so one of the v's goes away on the right side and the other goes away on the left. And sine theta is going to be 1 because our velocity and magnetic field are at a right angle. So that simplifies this equation to QB equals m times v over r. Now we can rearrange this equation and solve for r, and that's going to give us that r is going to equal m times v divided by the product of the charge and the magnetic field. All right, so a scientific piece of equipment that uses a lot of these principles is called a mass spectrometer. And what a mass spectrometer does is it helps us determine the different isotopes for different elements. So a mass spectrometer, the way it works is we have something called an ionization chamber. And in that ionization chamber, we place a sample of an element, and it's bombarded with electrons to give it a positive charge. So then we're going to have a region where we've got two parallel plates. And what we're going to do is we're going to charge those parallel plates. And the top one we're going to charge with a positive charge, the bottom with a negative. And that's going to create an electric field that's going to point downward between the two plates. Now we're also going to have a magnetic field that's going to run perpendicular to the page, in this case into the page. And what happens in this part of our mass spectrometer is when we run that charge through, it goes through undeflected. So let's explain why that charged particle moves through undeflected. So we're going to start by drawing a free body diagram. And we know that when a positive charge moves in an electric field, it's going to move in the direction of the field line. So we have an electric force that points downward. And we also know that there's a magnetic field and it's moving. So we can see our right-hand rule shows that the magnetic force is in the direction of our palm, which is going to be upward. Well, if it doesn't have any deflection vertically, that means that the magnetic force, that's going to be equal to the electric force. So that's why it doesn't deflect. So the magnetic force is equal to QVB, and that's equal to the electric force, which is equal to the electric field times the charge. Now we can see that the charge values are on each side, so that cancels out, leaving us with the speed times the magnetic field is equal to the electric field, or we can rearrange that to solve for the speed, and that's going to give us that the speed is just a ratio of the electric field to the magnetic field. So we can calculate the speed of a particle moving from the ionization chamber through the combined electric and magnetic field simply by taking the electric field divided by the magnetic field. Now the second part of a mass spectrometer is an area where we only have magnetic field. There's a detector that is where the charged particles can end up hitting. And what happens is once the charged particle enters the magnetic field, we know that the magnetic force is up, so it's going to move in a circular path. And the circular path, its displacement is just going to be from the point where it started in the magnetic field to the point where it hits the detector. And that's going to be the diameter of our circular path. So we have our equation for radius, and we know that that radius of our circular path is equal to the distance divided by 2, the diameter of that circular path divided by 2. So we end up with d over 2 is equal to mv divided by the product of the charge and the magnetic field. Now something that's important in atomic physics is a charge to mass ratio. So what is charge to mass ratio? Well, it's just as it says. You have charge to mass, so we could rearrange this equation and get Q divided by M, that's our charge to mass ratio, and that's going to equal 2 times V divided by the distance divided by the magnetic field strength. And 2 over D, remember that is just going to be the inverse of the radius, so we could use the radius of the curvature of that particle in the magnetic field. Now using this ratio is what led J.J. Thomson to discover the electron. So a lot of different discoveries were made by using a charge to mass ratio. So now we're going to transition to magnetic forces on current carried wires. So we have a horseshoe magnet. The north is on the bottom, the south is on the top, and we're going to run a wire in between the north and south of that horseshoe magnet. And then we're going to run a current through it, and we can see that that gets deflected to the left. So the current is coming out of the page, and it's moving from the back to the front. So what we're going to do to find the direction of the magnetic force and explain this is use our right-hand rule. So our thumb, again, is going to be aligned in the direction of the moving charge, in this case the current, Our fingers will be aligned in the direction of the magnetic field, which goes from north to south, so it's going to be up along our page, which then means that our force is going to be the direction of our palm, which is pointing to the left. So this is why our wire gets deflected to the left. And we know to calculate magnetic force on moving charge, it's just a singular charge times the speed times the magnetic field times sine theta. But now we have multiple moving charges moving across a distance per time. So we substitute the speed for distance over time. But we also know that charge divided by time, well, that's going to give us the current that is flowing through the wire. So we can rearrange that in I times d times b sine theta, but the distance is just going to be the length of the wire that's in the magnetic field. So our magnetic force can be calculated by ILB sine theta, where the Fm is going to be our magnetic force, I is the current that is flowing through the wire, L, that's the length of the wire that is in the magnetic field, B is the magnetic field strength, and then finally theta, that value is going to be the angle that is between the wire and the field, or the direction of the moving charge and the field. So let's look at an example problem. So there are two current carrying wires that are parallel to each other as shown. And we want to know what is the direction of the magnetic force for wire 2 from the magnetic field of wire 1. So the first thing we're going to do is find the direction of the magnetic field from wire 1 using the right-hand grip. We can see that when we wrap our fingers around the wire, we can see that the magnetic field on the right side of wire 1 is going to be directed into the page. Now, what we're going to do next is we're going to determine the direction of that force by using our right-hand rule for force. So we align our thumb in the direction of the current, our fingers in the direction of the magnetic field, and that shows that the magnetic force is the direction of our palm, which means that that force is going to be pointing to the left, which means that it's going to attract towards the wire 1. Now the next thing we're going to do is we're going to write an expression for the value of the magnetic force that wire 1 exerts on the section of wire 2. So we know that magnetic force on current carrying wires is ILB sine theta. Now we know that the magnetic field is into the page, and that's going to be perpendicular to the length of the wire in that magnetic field. So that means sine of theta is going to be sine of 90, and that's going to be sine of 90 gives us 1, so we don't need the part of sine theta. Now, the magnetic field is going to be from wire 1, so we're going to put a subscript of 1 on magnetic field. So we can use this equation to calculate the value of the magnetic field from wire 1, which means that we're going to have to use the current value from wire 1. So B1 is equal to mu naught times I1 divided by 2 pi, and that R value is going to be the distance between those wires. Now the current in the magnetic force equation, that's the current that is flowing through wire 2. So we're going to put a subscript on that I of I2. So magnetic force equals I2L times B1. Now we can substitute in for B1 our expression that we found for B1, and that gives us a magnetic force equation of I2 times L times mu naught I1 divided by 2 pi times the distance between those wires. And we know that that magnetic force, based on our right-hand rules, is going to be an attractive force from I2 being pulled towards I1. Now we want to also look at another question. How does this force compare to the values of the force that wire 2 exerts on wire 1? Well, we could go ahead and go through and use our right-hand rules for wire 2 and wire 1, but what we'd find is that it would be an attractive force as well, and it'd be the same value because all that would change in our equation is I1 and I2 would switch. And also, this is an example of Newton's third law. So wire 1 exerts a force on wire 2, pulling it towards it. Well, then the equal and opposite force to that is going to be that wire 2 pulls wire 1 towards it, so it's an attractive force between both of them. Now we're going to talk about magnetic fields inside a solenoid. So a solenoid is a coil of wire in a circuit that looks like this. So you just have loops of wire that are looped around something in a circuit. And this acts as a magnet when current flows through it. It also converts electrical energy into mechanical work. So if we look at a solenoid that's hooked up to a battery, so we have current flowing through that solenoid, what we're going to do is find the direction of the magnetic field using the right-hand rule. So if we look at the current, the positive charge flow is going to be moving downward in the front and upward in the back. So we're going to curl our fingers in the direction of the current as it's moving down in the front and up in the back. So we curl our fingers around the solenoid, and our thumb points in the direction of the magnetic field. So the magnetic field on that solenoid, we're going to have the north is going to be at the right side and the south at the left side, pointing in the direction of the magnetic field. Now, if we look at a simulation of this solenoid when we have charge flowing through it, we can see that the charge flowing through it, we have the magnetic field is moving around that and outside the solenoid and through the middle. Now, this is a simulation from Companion's 3D model. This is a solenoid. You can click on that link in the slides and it actually brings you to a simulation that you can click and drag and move so you can see different things. Now, to calculate the magnetic field inside the solenoid, the magnetic field strength is measured in Tesla. We need to know the current in the wire and measured in amperes. We also need to know the number of coils per unit length. So how many times does that wire wrap around in 1 meter? So if we know the total length of the solenoid, we can take the number of coils divided by the total length, and that would give us our N value. To make this an equality, we're going to multiply by mu naught, which is the magnetic permeability of free space. And remember, that value is 4 pi times 10 to the negative 7 Tesla meter per amp. So this is an introduction to magnetic force on moving charges and current carrying wires. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below, subscribe to my channel, Cavi Coaches, and follow me on Instagram and X at Cavi Coaches.